fascination with the red planet began with astronomers in ancient Egypt. The Babylonians and Greeks tracked the motion of the planet, and Galileo made the first telescope observations of Mars. Even today, when we look into the night sky and see the pale red dot above us, it inspires us to wonder about this nearby world. The question we have now is, how do we get there?
In the harsh environment of space, maintaining a livable atmosphere can be extremely challenging. Astronauts need reliable systems to provide clean water, breathable air, and stable temperatures, all while being millions of miles away from Earth. These life support systems must work flawlessly, while still mitigating their impact on crew operations. Unfortunately, and as of today, oxygen production systems for human spaceflight are not as reliable or as efficient as we need. Just as an example, if we want to send 4 astronauts to Mars on a return trip, today it will be more mass efficient and less complicated and less expensive to just store all this oxygen in a tank instead of recycling it from the cabin atmosphere. Part of the reason is that in order to separate gases from liquids in microgravity, we need to deal with the lack of buoyancy. And this lack of buoyancy forces the adoption of a series of extremely complicated mechanisms like centrifuges, valves, pumps, or water recirculation loops. That has been the state of the art as of today. But here at Georgia Tech, we are thinking about a disruptive new architecture, magnetohydrodynamic oxygen production. The term electrolysis describes the splitting of water into hydrogen and oxygen. To electrolyze water, you just need 3 things: some electrodes, an electrolyte to make water conductive, and some power. Here you can see 2 electrodes immersed in water that has been made conductive by means of an electrolyte. When we apply a potential difference between these 2 electrodes, we are closing an electric circuit. Charged molecules are flowing from one electrode to the other, inducing a current. Well, it turns out that in the presence of a strong magnetic field produced by these neodymium magnets, which are permanent magnetic materials, we can induce a Lorentz force, a driving volume force that moves the liquid in a given direction. With some engineering, we can exploit this effect to our advantage in space to produce oxygen for human spaceflight. Theo is going to explain you how we did that.
Since our overarching goal is reliable and lightweight oxygen generation for astronauts, it's worth examining why current technologies are insufficient for the Mars mission. As Alvaro shared, separating gas from liquid can be quite a challenge when you don't have gravity to assist. The pump and rotary separator, currently employed for this on the International Space Station, are plagued with issues. Pumps degrade rapidly with near constant use, lubricating materials expire after long-term storage, and the recirculation loop pressure can be unstable. Since astronauts are dependent on this system, spare parts have to be carried for failure-prone components. And what this would mean for the Mars mission is launching 4 or even 5 replacements for each unit. Plus, replacement activities cost valuable astronaut time during the mission. What these findings show us is that we require a new architecture if recycling water is actually going to be more efficient than just carrying compressed oxygen gas. That's where our magnetohydrodynamic design comes in. You might have heard about this in The Hunt for Red October, where Sean Connery's submarine supposedly employed it for a silent engine. And while not technically feasible at that speed and scale, we can use it in our electrolyzer. So in an alkaline cell, you already have current flowing between electrodes. Those are the orange lines. Then, if you place a magnet nearby, its magnetic field, shown in green, induces a Lorentz force on the fluid, which is shown in blue. If these fields are strong enough, the swirling motion generated in the drive is enough to force the fluid to the outside wall, while the gas, hydrogen and oxygen separated by a membrane, is forced toward the inside, where it can be extracted for use by astronauts. So, you might be wondering, what would this actually look like in the real world? Here's a subscale 3D printed mock-up of the prototype I'll show in a minute. You can see slots for the magnets, plus the electrodes are separated by electrolyte and a membrane, and we have acrylic viewing ports for visualizing bubble movement. If this whole thing sounds a bit far-fetched, don't worry. The Lorentz force is well characterized in the literature, and our lab has demonstrated this functionality in microgravity drop tower tests. The fact that phase separation is accomplished without moving parts is a big deal. By eliminating the riskiest components, we dramatically simplify the fluid handling architecture. And besides additional sensing and filtering on gas outlets, plus a new buffer tank to replace potassium hydroxide, this system is relatively similar to the currently employed oxygen generation assembly on the ISS, and it would interface with a Sabatier system in order to utilize generated hydrogen and reduce net water consumption. And here's what the Phase I work included. After assembling the drive and completing checkout tests, we performed experiments to validate the angular velocity as a function of the magnetic field and current density, or the current per electrode area. Looking down on the drive oriented horizontally, we observe swirling induced by the magnetohydrodynamic force, which, again, is produced without moving parts solely due to charges moving in a magnetic field. The hydrogen and oxygen bubbles form at the electrodes and move toward the center, where they escape to the fume hood. In the space architecture, it is this motion which will create a gas core and enable phase separation. This relationship among the magnetic, current, and flow fields is essential to guarantee function as expected in microgravity. And here are the results. With increasing current density, the rotation rate at steady state also increases as we expect. These values fit to within 18% of our magnetohydrodynamic analytical model. This model is part of an optimization algorithm which accounts for electrochemical, magnetohydrodynamic, and mechanical designs to reduce system mass and power consumption simultaneously. Additionally, the benchtop prototype validated aspects of design for manufacturability and design for assembly, particularly with regard to magnet insertion and fixturing. Some of these constraints will be essential for developing the multi-cell articles for the Phase II test campaign, as Alvaro will describe.
The result of this effort is a much simpler architecture that leads to a reduction in the number of components and spares, bringing down the total mass budget by up to 33% and the astronaut maintenance time by more than 20%. Together with a favorable microbial environment and an inherent stability in dormancy periods, these metrics enable regenerative life support in long-duration space missions. We now need to refine our architecture with an emphasis on design for replacement and repair, together with our partners at Giner Labs. We will carry out a 30-day endurance test of our system to assess its long-term degradation and thermal performance. We will also build and drop a full-scale MHD drive prototype at ZARM's drop tower to analyze and validate the low-gravity gas management design of our system. Together, these tasks bring us closer to TRL-6 and commercial infusion. The trip to Mars is the latest manifestation of humanity's never-ending passion for exploration and discovery. By developing reliable, efficient, lightweight life support systems, systems that we can trust millions of miles away from Earth, we are taking a leap in the right direction. We are excited here at Georgia Tech and Giner Labs to work with NASA to realize this vision.